We are back to chapter 28, 28.4, relativistic addition of velocities. What we're going to be doing for the rest of this chapter, for this day, essentially, is we're going to be now expanding relativity into Newtonian physics. Oh yeah. So thus far we've talked about three things concerning relativity. Did we record those last time? I hope we did. Let's check to make sure. Let's see what is that would have been 4.3. That's not what we want. We want the upload history. Let's see, we want to go look at Physics 1420. Physics 1420, 0403. So we did do that. This got deleted somehow. 0313. Oh, then we had spring break. Right. Apparently, some video got deleted from. Is this the first week back from spring break? No. So my video from last week got deleted somehow. I got to fix that. That's all right. I'll go back to it. But anyway, last time we talked about Einstein's postulates of special relativity. We talked about simultaneity and time dilation and length contraction. And now now Einstein. One of Einstein's postulates is that the physics would be the same. If we did this stuff, all the physics would remain the same. And so what we're going to show now is that the physics does remain the same. So the first thing we'll do is we'll talk about velocity addition. If you remember when we were doing relative motion in Newtonian physics, we had people paddling down a river. If the river was going 10 meters per second and the paddler was going 3 meters per second, then the boat would actually be going where the boat was going 3 meters per second relative to the river. Then the boat relative to the side of the riverbank would be going 13 meters per second. So that was just, the adding of velocities was really simple. If they're going the same direction, you add them. If they're going opposite directions, you subtract them. Simple. And that's what we call classical velocity addition. No big deal. Your final velocity relative to your stationary observer is equal to the velocity of your reference frame plus your velocity relative to that reference frame. Simple. No big deal. However, since the speed of light is constant in every reference frame and to every observer in any reference frame, then we have to make a big kind of change to this thing. And you might have guessed it, there's going to be a gamma involved, right? The gamma, remember that gamma is this 1 plus velocity squared over c squared. With relativistic velocity addition, it's not velocity squared over c squared. It's the velocity of your reference frame times the velocity of you, or the velocity of whatever it is that you're measuring the velocity of in that reference frame, or relative to that reference frame, over c squared. So so each one of these u, v, and u prime are all velocities. The u is the velocity of the object relative to one observer. V is the relative velocity between the two observers, and u prime is the velocity relative to the other observer. So the u's are velocities relative to observers. If you have one observer on the side of the road, it measures the velocity of something. This observer measures the velocity of something that's moving by. Let's see here. In this particular example, we're measuring the speed of the light of the headlights. So in this case,
Yeah, but I thought the speed of light was by itself because it never
You can measure the velocity of anything you want. It can be the speed of light, it can be the speed of a spaceship, whatever it is. But if you use the speed of light, this is what you're going to get. So this person measures the speed of the light headlights to be c. So the speed of the thing that he's measuring is u, and it has a value of c. This person also measures the speed of light of the headlights to be c. So u prime is also c, and then the speed of the car is v. So if you use this equation with those values, then you get c times c up at the top here, and you get v times c up here, and you get 1 plus v in the bottom, and you get v plus c in the top. So if you, you get 1 plus, yeah, that's correct. And what that's going to show you is that in the end, u is going to equal c, in other words, or it's going to show that u equals u prime in the end, or some such thing like that, if you do this particular example. In other words, it's going to give you what Einstein predicted, and that is that both observers observe the speed of light to be the same no matter what. In other words, this equation works in relativistic situations. This equation also works in non-relativistic situations, because in non-relativistic situations, the velocity of your time frame relative to the speed of light is going to be extremely small. So this number over here is going to be an extremely small number over an extremely big number, c squared. So this number is going to be 0, and this equation is just going to be v plus u prime over 1, which is exactly what the classical equation says, right? So this equation works both classically and relativistically. It just that the bottom approaches 1 as v gets very, very small. However, if you start looking at things that are more relativistic, then it starts to make a little more sense. So let's look at this spaceship problem. Spaceship problem has a laser light moving off of the spaceship, going towards the Earth and going away from the Earth. And we want to calculate the speed of the laser in each time frame. And if we do that, the speed of the laser in one time frame, we plug in c for u prime in each of these equations, and we solve it, and we find out that u, which is the other observer's speed of the light or the laser, is c, just like I mentioned before. So it comes out both ways correctly. Now, if we do something differently, which is like fire a canister off of a rocket that is not going the speed of light, and the rocket is going something close to the speed of light, like 0.5 times the speed of light, and the canister is going 0.75 c relative to the rocket, u prime is relative to the rocket, then what is the speed of the canister relative to somebody on the Earth? Well, you might think that it would be 0.5 c plus 0.75 c, right? Because that's what classical mechanics would tell you. If you fire a canister off of a rocket, and the canister is going 0.75 c relative to the rocket, and the rocket is going 0.5 c relative to the Earth, then you would assume that the person on the Earth would see this canister going by at 1.25 c. In other words, the canister would be breaking the speed of light. However, if you plug these numbers in, u prime is 0.75 c, v is 0.5 c, into this equation down here, and calculate u, which is the speed of the canister in the other time frame, which is the person on Earth, you will get 0.909 c. The canister does not break the speed of light, in other words. Doesn't come close. Well, 0.9 c is pretty close, but. And if it's going the other direction, it also doesn't do it. The other direction, if your velocity of your rocket is going 0.5 c and the canister is fired off backwards at negative 0.750 c, the addition doesn't work out either. Classical mechanics would tell you that the speed would be 0.25 in the opposite direction, or negative 0.25 c, but it's not. It's actually negative 0.4 c. It's actually moving faster than you would expect it to move. So velocities addition of velocities do funny things relativistically. And since one of the things that we do with addition of velocities is the Doppler shift, if you remember the speed of sound in the Doppler shift, when the fire engine goes by or whatever, and it changes the pitch of the sirens, right? This Doppler effect also does something in relativistic that's different than it does in classical mechanics. In classical mechanics, it changed two things. It changed the speed of the sound wave, and it also changed the wavelength of the sound wave. In relativistic mechanics, it does not change the speed of the light wave. It does not change the speed of light waves. But it does change the wavelength of light waves, and this is how it changes it. This is the equation for it, where you have the observed wavelength, you have the source wavelength, and then so the observed wavelength is the one that's going to be shifted. The source wavelength is going to be the one that is going to be is the one that's going to be measured from the moving time frame, from the moving object, in that time frame of the moving object. And then u is going to be the speed of the moving object, and c is going to be the speed of light. Plug those things in and you can get either wavelength observed or frequency observed using either one of these equations. They're not the same equation. Notice that the plus and minus signs are switched. But when we do this, what we'll find out is that as you're moving towards things, the frequencies increase or the wavelengths decrease. The wavelength gets shorter or the frequency gets higher. And as you're moving away from things, or they're moving away from you, either way, then you get an increase in wavelength or a decrease in frequency. In other words, things start to shift towards the blue end of the spectrum when you're going towards them or they're going towards you, and things switch towards the red end of the spectrum when you're going away from them or they're going away from you. Okay? And you can measure that shift. So in this particular case, there's a radio wave that is being emitted by a galaxy, and the radio wave has a wavelength of 1.7 meters that is being, well, actually they're saying that the galaxy is emitting a wavelength of 0.525 meters. That's not the way it's done. Normally what we do is we observe this one. We observe the 1.70 meters. That's the thing that we observe, and then we calculate the wavelength that it is actually emitting. And actually, that's not even the way that we do it. The thing that we're always doing when we measure wavelengths that we're often doing when we measure the wavelengths of things now, is we usually measure the wavelength, and then we plug in what it should be, what the wavelength should be, and we calculate the speed of the galaxy moving away. Sometimes we know what the speed of the galaxy is moving away. We can do that by using parallax. You remember the parallax we did in optics? Yeah. Parallax can tell you how far away something is. Since we know how far away the moon is, for example, or we know how far away certain stars are from other measurements, we can use the parallax of stars that are further away to determine how far away those stars are. As the Earth moves around, the relative position of those stars move around, and those angles can tell you how far out those stars are. The more they move, the further they are, right? And so if you can use that parallax to figure out how far away galaxies and stars are, and if you know how far away they are, then you can determine how fast they're moving. Because according to some of the theories that we have with the Big Bang Theory, the galaxies that are further away are moving at a different speed than the galaxies that are closer into us. The ones that are further away are technically moving away faster than the ones that are closer into us. And they have theories for determining how fast they're moving relative to us. Then you can plug in that speed right here. You can plug in the observed frequencies here and calculate what the frequency should be. And if you know what the frequency should be for that galaxy, then you can start to figure out some things about that galaxy. Because what the frequency should be, or what the wavelength should be, determines the behavior. Galaxies emit certain wavelengths of frequencies because of the way that they're doing things because of what they're made of, because of how they're moving, what their gravitational structures are, and things like this. Now, with the advent of the discovery of gravitational waves, we should be able to start doing this with gravitational waves as well. They already have.
Gravitational waves, what makes the red light shift?
No. No, the red light shift and the blue light shift comes from the galaxies actually moving away from us. They're literally moving away from us at a speed close to the speed of light. So they're moving, the galaxy is expanding very rapidly. So we're on one edge. So the galaxy, you could think of it as a great big balloon, whereas it started off as a single point and then exploded outward. And everything that is formed on this spherical shell. We're on one part of the shell and everything else is on other parts of the shell, right? So that's the way you can think of it. Being one monster what? Snow cone?
Snow globe.
Snow globe. Well, we're on the edge of a snow globe.
Snow
We're not-
is constantly expanding.
We're not in the middle of the snow globe. It's more like a balloon that's being blown up, right? And that's something that is really not well understood by the general populace. I mean, the general populace assumes that the galaxy is some one continuous thing from here to the other end of the universe, right? But what's really going on is our galaxy is just one tiny little speck on the edge of a balloon. And the universe is this kind of two-dimensional thing that is smeared or stretched around a three-dimensional balloon. Probably a better way to think of it. Anyway, is there something at the center of it? Don't know. Why? Well, because when you explode a bomb, there's nothing at the center of the bomb. If you explode a bomb, there is no residue of the bomb at the center of it. Okay? Unless there's ground there to stop it from going somewhere. So if you explode a bomb in the middle of the air, all of the residue of the bomb leaves that space.
Yeah, but there's still something there.
Well, yes, but we're assuming that there was nothing and a bomb exploded.
Yeah, so if you do it in a vacuum and explode a bomb, there will be nothing at the center. Right? You're a bomb expert. You know that bombs explode
Yeah,
from the inside
there's
out.
something at the center, air or lack of.
But if it's a vacuum, then there will be nothing. It will be just a vacuum.
There's a vacuum at the center.
But is a vacuum something?
Yes.
Well, you are enlightened because there are many physicists that believe just like you do that vacuum is something. I also believe that that could be true. But there's no evidence that vacuum is something.
Other than a vacuum, there's probably.
There's a lot of theories about it, but they haven't been able to prove that it's true yet.
So basically, there might be.
So you're on your way to a Nobel Prize. Just believing that puts you on the step to that. Which is really kind of weird because if you go back 400 years or 200 years ago, maybe even 100 years ago, nobody believed in a vacuum. It was hard for people to believe that there was nothing between the nucleus and the electrons, that there's not air between them. Air is bigger than that. Air is nitrogen, which is bigger than the space between, bigger than the space between the nucleus and there's not a single nucleus and electron combination on the periodic table that's bigger than nitrogen. Nitrogen molecule is bigger than all those things. So there's no air at all between the nucleus and the electrons in an atom. So there's just nothing there, and we call it the vacuum. But now there are there are physicists that are trying to develop a theory that says that there is something there, but it's not something that in the same sense that we understand something. And they call it the, let's see what they call it. They call it the I can't remember what they call it. If we look up vacuum theories, we'll be able to find it. Hey, there's my chopsticks I was looking at.
Because if you could take already in vacuum, right? So if vacuum is nothing, then you can take this room, seal it up, put a vacuum in here, nothing, nothing. But
Yep.
it's still here. It's still
So the superfluid vacuum theory is one of them, also known as the BEC vacuum theory. Bose-Einstein condensate. That's a fairly new one since the Bose-Einstein condensate is fairly newly discovered. There's another one called I can't remember. Yeah, so dark energy is one of the. So there's superfluid, there's BEC or BEC or superfluid vacuum theory. There's one that's something that has to do with wave theory or something. I can't remember what it's called, but anyway, it's the I can't remember. It's people that just like sitting in front of computers or writing things down. They come up with these theories because they don't want to actually do anything, so they don't. Anyway, so back to what we were doing here. The Doppler shift, relativistic Doppler shift, is definitely a thing. And like I said before, we could use the same idea with gravitational waves, because gravitational waves also travel at the speed of light. They're not light waves, and their wavelength is much longer than the light waves that we normally deal with. The wavelength of a gravitational wave is super long, and it's not a light wave. It's an actual distortion of the universe. It's a distortion of space and time. So the wave is actually, you could think of it as compressing and decompressing the universe. The universe itself is vibrating instead of something vibrating within the universe, right? But they have figured out a way to detect that, and because they figured out a way to detect that, they can do that. So have we talked about how they detect gravitational waves yet? Oh, let's do it. Because it's not in this book yet.
Right? If you take the vacuum and you take all your equations, right, and your equations have distance measurement, well, there's distance in vacuum just like there is outside of the vacuum.
So what you're saying essentially is that space itself is a thing. And I agree with you, and so do most physicists. But we've not been able to detect anything within that space. So in order for us to believe that there is something there, well, it's measurable as long as you put something in there to measure it.
No.
Yep. You have to put either a light in there to measure it or a ruler in there to measure it. If you're measuring the outside, you're not measuring the space. You're measuring the container that's holding the space. So to measure the space, you have to put something in that vacuum, which destroys your experiment, right? Whenever you measure something, you have to do it without affecting the thing you're measuring if you want it to be a true measurement, right? So we have to measure it in some other way.
The space where the theory is the two things you should try to measure apart.
Well, how do you define space? Now you've defined space as two different things. Something that is contained by something and something that's always there. If something is always there, you didn't have to contain it. So we could remove the container and it would still be there.
Mathematical problem, one doesn't work for another one, the other one does.
That's a good question. We're getting into philosophy here, which we don't want to discuss right now. Because then we take apart this whole class and just say we didn't need to take this class anyway because it didn't exist, right? If physics students and teachers don't meet in a classroom, does physics exist? Anyway, the LIGO experiment was done. Here's the experiment. So you can see here there's these super long, essentially tubes, pipes, and then there's this building here. And if you remember from last time, we looked at this one, the Michelson-Morley experiment. The Michelson-Morley experiment is the same experiment, except in this one they went around a table and came back to a point. In the LIGO experiment, they go all the way down and come back, and then all the way down and come back, and then they do their interference here. Okay, so they're shining. Let's see what. I can't remember what the LIGO beam is. I believe it's a laser beam, but I can't remember if it is.
LIGO's laser.
The LIGO, yeah, LIGO is a laser, and it's a 808 nanobeam laser, so it's a near infrared light laser, and it's a 4-watt laser, which is pretty big. We built a 1-watt laser, 1-watt 800 nanometer laser when I was in college. But anyway, with the Michelson-Morley experiment, they just used visible light, and they went around this thing and they measured the interference because one of the arms was going faster than the other arm. They expected there to be a path length difference, you know, there. In this case, they had to make them so much longer because the wavelength of, let's see, view image. The wavelength of this thing is so much longer. So the wavelength of gravity waves can be miles and miles long. So in order to detect a change in that path length, you have to have a much longer path. And the path of this laser beam is actually even longer than it looks. Because if you look halfway down this path and all the way down this path as well, not even half, it's about halfway actually. Halfway down this path you see another building. Down here there's another mirror and then another mirror down here, so that it bounces back and forth several times down here and then comes back. So the effective length of these things is, I don't know how long, let's check. LIGO beam effective length. I'm not the first person that's asked this question apparently. LIGO beam effective length. So the effective length of the LIGO beam is yeah, so it's called a Fabry Pro interferometer. We actually made one of these back when we were, and right here they actually talk about it being similar to Michelson's interferometer. So this is the basic Michelson interferometer. The LIGO interferometer has these extra mirrors in it, so it bounces back and forth and back and forth. Oh, so the effective length is 1,120 kilometers long. So 144,000 times bigger than Michelson's interferometer. Okay, they're called Fabry Pro cavities that do this, and this is something that was not done in interferometers very much until very recently. In fact, when I was doing it at BYU, we were doing some of the first work on that. So it's something that is fairly new, and they took that idea and made it huge. And so Fabry Pro interferometer being used in the LIGO array, this LIGO interferometer, creates this huge path on either side. And then what this is designed to do is it's designed to measure if space gets shorter, if the universe gets shorter and longer, or if it's vibrating at all. It will vibrate differently here than it does here, just because they're at a 90-degree angle, and because there's no way that we lined it up exactly so that every distortion in space and time is going to just be the same on both. It's never going to be the same on both. It's absolutely impossible. No, the Earth moving has nothing to do with it. The Earth moving will not change this at all, because it does not change. Moving things does not change the path of light. We learned that with Michelson, right? The Michelson interferometer didn't change the path length. So it doesn't matter if the Earth moves. That won't change this at all. The gravitational effect of the Earth moving will not change this, because the gravity of the Earth.
Earth is moving through space.
So it won't line up the same.
Oh yes, because Earth. Yeah. Okay. So because Earth is rotating and because it's moving through space, it also, yeah, that's also true. So there's so many different things that you could say that this would never ever line up so that it would just be exactly the same on both of these things.
And look, they got a trout stream right beside it.
They have a what?
Trout stream right beside it.
On the left.
A what?
A trout stream.
Oh, a trout stream.
As far as physicists suggesting something to do, well,
It kind of looks unnatural. I think it's not a stream. I think that's a canal. So it's probably catfish. Trout don't like canals so much. Catfish do though. Trout like a lot of moving freshwater. Catfish, good stuff. You can get a big catfish out in these canals. When we first moved here, I went on a bike trip with the Boy Scouts, and we stopped by these fishermen who were trying to pull this catfish out. That they had 3 guys on this thing. 2 guys? 3 guys? I think it was 3 guys on this thing, and one of them had both his arms around it inside the gills. He had both his hands in the gills and both his arms around this thing, and it was going from like just below his chin down to his knees and a little bit further. And he couldn't pull it out of the water. He was like bracing his feet against big old rocks on the side of the canal and trying to heave this thing out. And the other guys were trying to pull it out, and they couldn't get it out. They had like a rope on it, you know. They were trying to pull this sucker out. It must have been a 100-pound fish. It was insane. They invited us around for a fish fry. I didn't go. I should have. But
Hey, speaking of which, I got trout that I thought out yesterday in my refrigerator. Do you want back of it?
Mom will need it.
my wife would get really angry if I brought fish into the house right now.
I think that is a yes.
You gonna take it as a yes?
Yeah.
Not right now. Not right now.
Okay.
I don't have time to cook things right now because I'm working on my house a lot. And if I brought fish in and started cooking and not working on my house, I'd get in trouble.
It'd be like
And she doesn't let me cook fish in the house anyway. I always have to cook it outside. So
Make Packer do it.
it's going to be snowing this weekend. Don't want to mess with it. Besides, I really prefer my trout fresh out of the water. I don't like it frozen. Frozen trout to me is not appetizing. Fresh trout is. I can eat other fish. Other fish freezes better than trout.
Yeah.
Like salmon freezes really well and other things, but trout gets kind of takes away the appeal for trout.
I just sort of assumed that salmon froze themselves in the rivers each year, so it's just a natural way for their life cycle.
You know what's funny? We're way off topic.
Anyway, so this is on topic because the gravitational waves happen because that we detected them because Einstein predicted they would happen. When Einstein went through his theories, he said, if light can't change, then time and space must change. We've already determined that time and space change. That the length of space contracts and that time dilates. But really what's going on there, it's very much like electromagnetic waves, where you have electric wave in one direction, magnetic wave in the other. Well, time and space are kind of like that, where space and time wave, they undulate. And when it does that, it actually makes this path shorter and this path longer, or vice versa. So they're going back and forth constantly. And if you have a laser going down this 1,000-kilometer path and another one going down this 1,000-kilometer path and coming back here and interfering with each other, you're going to see an interference pattern. And the really interesting thing about this is the interference patterns that you see are really, really low frequency for light. So they're not that easy to see in an interference pattern. However, if you connect them up to a speaker, you can hear them. They can actually be easily converted into sound because sound wavelengths are much longer. So if you connect the electrical signals that you get back up to a speaker, this is what you get. So let's take a look at the LIGO sound blip. So they actually listen for these things. They don't necessarily wear headphones and listen, but they have a computer listening for this sound blip.
They're listening to the universe shift.
That's right. They're listening to the shift, the waves in the universe. And this is what they heard at the same time at LIGO Hanford and LIGO Livingston, right here. So this is just... Hear that? So that's it. So when that blip comes in, that's when they know they've detected a wave in the universe or a bend in the universe, because they've connected these two lasers up to they connected them to a computer that detects that blip. And so that's really kind of cool because You can hear it, and I mean, it happened. The reason that it happened was because of two black holes merging. The only way that you get a blip that big or a wave that is detectable is if two massive gravitational objects interacted with each other in some way to make a bigger gravitational object. And this is an artist's rendition of what they think would have happened. So this is what it would look. This would look like if two black holes were rotating around each other, and then eventually, this is of course in slow motion. Eventually, they get closer and closer and going faster and faster and faster, and then they merge into one black hole. And when they merge into one black hole, they create a big wave in space. That wave happening, you can see this bending out here is the waving in space. And that biggest wave happened right as they combine right here. This whoop, right there. See that? That's what they detected, is that that dissipated out into the universe. Of course, if it happened close to us, it would have, well, it might have done something really bad to Earth. No, we don't really know what it would do to Earth, honestly. But we assume that a huge gravitational pulse to the universe like that, the closer you are to it, the more dangerous it would be. But that was quite far away.
Wouldn't it like seriously contract and expand different parts of the
Well, what it does is it expands and contracts the universe and everything in it, including atoms and time and everything. So we don't know.
Would you even notice the effects though as you?
We don't know. We don't know what it would be. There are plenty of theories, but to test those theories, we have to go close to a black hole, right? The effects to us here, we don't even know what they were. We don't know if it affected us in any way here, except that we know that we detected it. So it's a new science. So this is exciting stuff. But another thing that has been discovered is that it used to be thought before this project came about. It used to be thought that black holes were really quite rare. That they were these exotic objects that were very. There was very little evidence of black holes before this. The only evidence that we had of black holes before this was sometimes when people were looking out into the sky with their telescopes, they saw two identical stars up in the cosmos there, and they said, "Why are there two identical?" They were exactly identical. When one of them would change, the other one would change at the exact same time, and they couldn't figure out why they had these identical stars. And what they discovered was that they were looking at the same star, but that star, the image of that star had been doubled or had been bent around the gravitational field of a large black hole in between the observer and the star. So that you have this star, and you can take a look at that.
The reflection and the.
Well, you're seeing two images of the star. You're not actually seeing the star itself. You could think of it that way. Or you could say you're seeing the star itself twice, but that's actually what it would be. But the evidence of existence of black holes. Let's see if they talk about that. Hubble images right here. No. Let's see. There's a black hole. Escape velocity.
Look at images on the top.
What images? So here's one of the things that we have. This is one of the images that we have of a black hole from. This would be from, I believe. So this is not an actual video. It's many pictures that have been stitched together to make a video. But these pictures are showing that we have all this stuff that's rotating around this blackness. And then right in here you see this little ring, and you see this little thing here. right? So this is evidence that there is something that is a lot of gravity, so it has a lot of mass, but we can't see it. And the reason we can't see it is because it's so massive that even light is attracted to it. The gravitational pull is so strong that even light pulls into it. And that's another thing that Einstein said, is that light is pulled into black holes. Well, if you're outside, if you're near the black hole, but not close enough to the black hole to be pulled in, you'll just rotate around it like you would around any star. And that's what's happening to all this stuff. But the reason there's not individual planets around it is because all this stuff is experiencing such huge gravitational shear forces. In other words, it's got a lot of tidal forces, like the things that create our tides from the sun and the moon. Those tide forces aren't just pulling the oceans, apart. They're pulling the entire planet apart, or the entire star, or whatever it is. So this is just junk out there in space. Things that have been ripped apart, stars and things. And there's smaller pieces of stars, smaller stars and things in here that are just rotating around this black hole. But there's this point out here, the event horizon, that nothing escapes. Light doesn't escape, nothing escapes, and that's right in here. In between here and here, things get sucked in. Essentially, they get pulled in closer and closer until they get to the event horizon where nothing can get out. Inside here, things can possibly get out if they're going fast enough, but they have to be going pretty dang fast. So light can get out of here, and that's why we see this object in here. Now, if you had a star that was on the other side of this black hole, right somewhere in this region, you would probably see it through here. But you would see one image of it here and another one here, because the light of the star would actually bend around the event horizon.
Why don't we see that as why isn't it like a ball instead of like a flat circle?
It's a flat circle because it's three-dimensional. You'd assume you'd see a ball because you assume that we would be able to see it from some side or another. But really, we're not really actually seeing it. What we're doing is we're detecting it. So we can detect it in the dimension that we're looking at it. So we look at things in a dimension. We can't see from the side if we're looking from this way. So we only see black holes we only see the evidence of a black hole in one dimension. And of course, it happens in 3 dimensions. But we can only see one dimension of it, or 2 dimensions of it. So if you looked at it from this direction, from up here, you would see a similar thing going on. Yeah, a similar thing. Not necessarily the same thing, because this object might not be rotating in that plane.
Yeah, but still the same circle.
Yeah, it may be a different shape. We don't really know. So that's one thing that gives us evidence of black holes. There are other evidences of black holes as well. Let's see if we can find another one. Anyway. But anyway, they thought they were very, very rare, because seeing this kind of evidence is rare. It's difficult. You don't often see this kind of thing happening out there. But with the LIGO observatories, now that they're up and running, there are 3 of them now, I think, maybe 4. Now that they're up and running, they have detected black holes like all the time. They're detecting them constantly. They've detected at least a dozen at the center of our galaxy, which we've always suspected is the case. We've always suspected there are black holes, or a single huge black hole at the center of our galaxy that holds our galaxy together. That's the gravitational force that holds it together. They've always assumed that, but they've never been able to detect it. Now they've detected at least 12 separate black holes that are different black holes, but they've also detected that they're all possibly orbiting another single humongous black hole. That they're just kind of little planetary black holes. So it's kind of exciting to learn this.
An object dense enough to get a star to orbit around it, and it's orbiting something else.
Yep. Yep.
Like a hair on the back of an amoeba.
Not even that.
Hair on the back of an amoeba, on the back of a flea, on the back of a dog, on the back of whatever. Yeah. It really gives you an idea for our galaxy, the Milky Way galaxy, which you gotta love it. Why would you call it the Milky Way? Well, we just do. So the Milky Way galaxy being what it is, you can see it at night, particularly in places where it's, I mean, this is what the Milky Way galaxy looks like if you have a really good night, and it's a really good, it's a really good night for it. If you're at high altitude, I have seen this before, and you go, "What the heck is that?" Because you're like, "What are these clouds? I thought it was a clear night. Those are not clouds. That is actually stuff. That is space dust, space junk that is between us and the arm of the galaxy that we're looking at. As we're looking at this, we're looking essentially from our little corner of the galaxy in towards the center of the galaxy, and we're looking at all the arms overlapping. And this is all the junk that's in between us and that. All the stuff floating around out there. Okay? So if you're ever up in the mountains, and up in the mountains matters because you want to be high in the atmosphere and far from a city, so that there's not ambient light around, and it's of course there's no moon, it's a new moon, or it's the full moon is set, or whatever it is. This is a beautiful thing to behold. It's just really phenomenal, and I've only seen it. And the one I saw it looked more like probably more like this, or something similar to that. So it wasn't quite as dramatic as that one picture I was showing you. Yeah, I would say it was probably kind of like this or that. But it is still just a phenomenal thing to see. There will be so many stars in the sky when you see this. If you see this, there will be so many stars in the sky that you will not be able to pick out a single constellation, because it will be so bright out. You'll think that there's a moon out, but there's no moon. There's so many stars in the sky. It's just phenomenal. It is amazing.
That stay in Nebraska.
In Nebraska, you can see it if you go up north, away from the cities. Go up north, away from the cities. We're at high enough altitude that you can see a pretty good Milky Way. It's pretty nice. It's not phenomenal like it would be up in the mountains, but you can see it. Go up into the mountains of Colorado, northern Colorado, especially getting away from Denver. Definitely going to see it. Wyoming, you're definitely going to see it. So, what's that? I saw it. The first time I saw it was in California, up in the mountains near Yosemite. And man, it is beautiful. But essentially what's going on is, this is what's going on. Here is the Milky Way galaxy. We are out at the kind of the center of one of these little tiny arms, not one of the big arms, one of these little tiny little things out here, right? This is where the center of it is, and where those black holes are happening. You can see there's a big bright spot there, and rightly so, because the concentration of stars there is so much higher. There are so many more stars there because they're being attracted by those black holes. We're way out here where nothing really is happening. We're in the boonies. We're the rednecks of the galaxy. Out in the middle of nowhere, living our little boondocks lifestyle. So, it's really quite amazing what's going on.
Just space
Space Hicks, yeah, I like that.
Speak for yourself. I'm
Yeah, Scott's a space Billy. He's a space Billy. Okay. All right, so now we've learned about the Doppler effect and about relativistic addition of velocities. Let's move on to the next two things, which are relativistic momentum. And you can probably guess how it works. Add a gamma to it, or multiply a gamma to it, right? Usually momentum is mass times velocity. Ours is going to be gamma times mass times velocity, where velocity, again, is shown as u, because we have so many velocities we have to deal with. We have the velocity of the object that we're trying to measure the momentum of, but we also have the velocity of the relative velocity of the time frame that object is in, and then the other time frame that we're measuring it from. So we're going to have three velocities involved in many of these cases. So in this case, we have the v is the velocity between observers. So v is going to be the relative velocity between two observers. U is going to be the velocity of of the thing that we're measuring the momentum of. And then c, of course, is the velocity of light. And then our momentum now is gamma m times u. The interesting thing about this particular equation is it has a very interesting result when you go through the theory. And the interesting result as you go through the theory is that the momentum of an object increases, let's see, so as you get closer and closer to the speed of light, as u comes closer and closer to the speed of light, then this becomes closer and closer to 1, right? Then you get 1 minus 1, which is 0, and you get 1 over 0 for gamma, which is what? What's 1 over 0? Infinity. So if you have infinity times mass times velocity, what happens to your momentum as you get closer and closer to infinity? So momentum is something that must be conserved. Can momentum get to infinity? No. If momentum is conserved, there is a finite amount of momentum available in the universe, which means the closer and closer that something has mass gets to the speed of light, the more and more force it requires to make it go faster, up into an infinite amount of force required to get to an infinite momentum. So the faster something goes, the more force it needs to go faster, up into an infinite amount of force. So can something that has mass ever reach the speed of light according to this theory? No. Now this is often confused with or misconstrued as mass getting more and more and more as you get closer to the speed of light. Even us physics teachers say that to help people to understand it. But really what happens is momentum. The momentum required, or the momentum that is, so the force that is required to reach that next state of a momentum up to infinite momentum as you approach the speed of light, is the thing that increases as you get closer and closer to the speed of light if you have mass. If you have mass, the amount of force required to make you go faster goes to infinity as you approach the speed of light. And so that is why something that has mass can never reach the speed of light. Right? This has interesting religious connotations, actually.
So you're saying that at the very center of the biggest black hole would be one atom that's in there just moving at the speed of light?
Well, it couldn't be an atom because an atom has mass.
It could be an atom moving almost the speed of light.
It could be particles moving at very close to the speed of light. That is true. But it could also be some other thing that we don't know about. It could be some other, so it's a massless thing, some energy, some form of energy. So many forms of energy have no mass associated with them, like light. And light can travel at the speed of light. So if you can figure out a way to make light rotate in a circle without going anywhere, then sure. Maybe dark energy has this property, has this ability. We don't know much about dark energy.
But light does bend around gravity.
Light does turn in gravity, and we're going to learn how that works here in a minute.
And then,
Well, it's actually easy to understand why light turns in gravity. We already know that space bends and we already know that space contracts and expands, and in 3 dimensions that means space bends, right? Light travels through vacuum, it travels through space. And if space bends around gravity, then light bends, because light follows the space, right? So that's why light bends near gravitational poles. We'll learn more about that in a second. So, we know that we now have this relativistic momentum. You use the gamma factor to calculate relativistic momentum. And what that's going to mean is that nothing that has mass will ever reach the speed of light. It also has some not funny, but interesting, I would say, religious connotations, because there are many religions that represent their deity as light. In the Christian religion, it's the most obvious, where in the scriptures it literally says, "I am the light," right? And if you're the light, if you're light and not a massless thing, not a mass particle, not something made of mass, then of course you can reach the speed of light. And if you can reach the speed of light, then all of a sudden space becomes a single point and all time stops. So then you're infinite. You don't experience time. Time is all one thing to you. You know everything because you can see everything all at once. And everything is all right at one point. So you're omnipresent. You're omnipresent, you're omniscient, and you're eternal. Which is exactly what the Christian religion believes about its deities, right? But other religions also believe similar things. That when we die, we become light, or we go to the light, or something like this. We become this spiritual light being, this being that has no matter to it. So that's kind of interesting to think about religions having this connection to physics. Because there are many people that say religion is just this, is obviously just something that man made up because they couldn't accept dying or something like this. I am not one of those people. I am one of the people that believes that there is something that we don't understand about this universe, and that I think that religion has an understanding of. And that through these things we have been given a little bit of that understanding. So it's just interesting to think of that in my particular. And I'm not the only scientist that believes that. I would say, from my own experience and from studies that have been done, roughly 50% of scientists, including physicists, in fact, physicists are a little bit more than 50%, roughly 50% of all scientists are actually quite religious and believe that there is something more, some higher power and organization and whatever else you want to call it, in the universe. So that's not by any means a strange way to think. In fact, I met a Nobel Prize winner who was known as the religious or the faithful Nobel laureate because of his speeches that he gave after he'd won the Nobel Prize about religion. Anyway,
Is that one you played frisbee with?
no, it's a different one. I played frisbee with a Nobel Prize winner.
So if you could take one particle and get it close to the speed of light, how much energy would that take?
Well, you couldn't do it because it would take more energy than it would take an infinite amount of energy, more
Well,
energy
just
that's
close.
available.
Close to
If you get it close to the speed of light, then
it. 99.99999.
the more nines you put on there, the more impossible it becomes. Because there is a finite amount of energy that the universe began with, and that the universe has at this point. And that can be actually estimated from lots of different measurements we've taken of the universe. So we can actually tell how much energy is in the universe to some, it's approximately.
Yeah, but once you get it there, isn't it easier to keep it there?
Once you get it there, it stays there on its own.
Right, black hole.
No.
One particle moving close to the speed of light.
No, it's not. A black hole isn't created by a particle moving at the speed of light.
How do you know?
Well, good thing. There's no theory that suggests that. There's nothing that would suggest that it would be that, because a black hole is a gravitational well, not an anomaly. It's what we call a gravitational singularity. And singularity is an infinitesimal concentration of
If you get a
infinite
particle
mass.
moving that fast, how do you know what kind of energy it put off?
It's not about the energy; it's about the gravitational. It's about its gravitational singularness. I don't know. It's about its gravitational concentration, is what it is. So that's what a black hole is all about. Energy of a moving particle is a different thing entirely. So they both have energy, but their energy is in very different forms. A moving particle, its energy is contained in its kinetic movement. For a black hole, the energy is contained. You want to see how much we can't get done today, don't you?
All right, let's move on.
All right. So now let's talk about energy. So now we talk about relativistic energy. And not surprising, it looks a lot like energy we've seen before, except it has this gamma in it again, right? Except there's also one other thing missing. Kinetic energy before this had the 1/2 in it. This one does not. So instead of 1/2 mv squared, 1/2 mv squared, it's gamma mc squared, right? And now also there's not a v there or a u, it's c. The v is in here, right? So if you want to calculate the relativistic kinetic energy of an object, you use this equation. However, this equation also has some interesting implications. It actually splits the energy into two things. When you break down this equation, you find out that there's one part that says that there's one part of energy that is just mc squared. It's just the mass times the speed of light squared. This is Einstein's famous equation, E equals mc squared. And this is exactly where it came from. When he was calculating the energy in his relativistic theory, it broke down into two energies, one that said E equals mc squared, and one that was E equals mv squared, essentially. So you had an mc squared part and an mv squared part, right? This one is what we call the rest energy. So the kinetic energy is pretty much, it looks a lot like it did before. It has this kind of mv squared thing to it. This one does not have that v squared in it. It is the same for every mass because c is the same all the time. It's the same equation for every mass. You just plug in whatever mass you have and you get this thing. So what is that associated with? And Einstein says since it's not directly associated with velocity, it is associated, it's an intrinsic part of the particle, and because mass is in there, it is directly related to the mass of the particle. So what he said is that every particle has energy associated with it that is directly related to its mass, how much mass it has. And they said, and we say to ourselves, well, how do you get that energy out? Well, you have to change the mass of the particle to do that. You can actually release this energy by lowering the mass of the particle. You can convert the mass into pure energy if you want to. Well, not if you have to do more than just want it. It's a very difficult process. But it can be done. Where is that energy residing in the mass? I mean, where is it hiding in there? It turns out that they discovered that as well. As they were discovering what atoms were made of, they discovered the children of this Marie Curie here, call her Mary Curie, but her name is really Marie Curie. Her two children, which are below her on the bikes there, I believe that's them. Maybe not, I can't remember. That might be the Becquerels. But anyway, her children discovered the neutron. And it turns out when the neutron is present inside of atoms, there's an increase in mass that's difficult to account for. And it actually has to do with the bonding between protons. The bonding between protons is caused by the presence of neutrons. So you can't have two protons together without at least one neutron. Like helium normally has two protons and two neutrons. It can have one neutron, but if you take away that last neutron and you just have the two protons there, that helium atom is not going to be helium anymore. Those protons are going to repel each other and they're going to become hydrogen. Okay? But if you add neutrons to things, you can start adding protons to things and they'll stick together. Neutrons act as kind of the glue, and when you put them together like that, you start getting mass that's not accounted for. You have more mass with the protons and neutrons together than the protons and neutrons have separately. Okay? So for some reason, putting protons and neutrons together creates extra mass. And this extra mass is due to the bonding that the neutrons create. The bonding absorbs energy from the surroundings. It pulls in energy from the surroundings and turns that energy into mass. And to release that, you have to break apart atoms and release some of that energy and get rid of some of that mass. And that was done for the first time with uranium. They tried to add an extra neutron to uranium because they noticed that when you add extra neutrons to things, you can make new atoms, actually. That neutron will turn into a proton. So they said, we'll add one neutron to uranium and see if we can make a new atom, a bigger atom than exists in nature. Well, turns out they split it and created a nuclear bomb. And then they released all that mass. They lowered the mass of uranium and created two new atoms, actually, two smaller atoms. And that mass turned into energy. We'll learn more about that in a couple of chapters, but it is part of this theory. It came from this theory. So if you want to calculate this energy, which we call the rest energy, the energy of the particle when it's at rest, just from the mass, you just plug in the mass, m times c squared being 2.99 times 10 to the 8, or they use 3.0 times 10 to the 8. It's pretty simple, not hard to do. So this rest mass actually plays a role in every kind of energy transfer, even like a battery. But the amount of mass that you lose when a battery gives out energy is super tiny. So they go ahead and calculate that change in mass from the energy here that they're giving out. So you have a battery that's giving, you have a 20 kilogram battery, and it's can move 600 ampere hours, which is which can be converted into energy if you multiply the amount of charge times the 12 volts. So amp hours times volts, you got to figure out how many coulombs that is. So they do that here. They calculate the amount of. So they actually just take the amp hours times the volts and divide it by c squared to get the change in mass. So this top part is the energy. This bottom part is the c squared. Rearranging the equation to calculate the mass. The change in mass ends up being 2.88 times 10 to the minus 10 kilograms. Very, very, very tiny amount of mass. Then if we look at the kinetic energy part of this equation, which the total energy is the E equals gamma mc squared. The rest energy is E equals mc squared, or E naught equals mc squared. And then if you manipulate the equations, you find out that the net work equaling E, the total energy minus the rest energy, gives you this gamma minus 1 mc squared, where the total energy before, total relativistic energy was gamma mc squared. So if you take gamma minus 1 mc squared, you get kinetic energy relativistic. So they've just gone through and done the math for us. What they've essentially done is they've subtracted off the rest energy, which is this part, or the rest energy part. They've subtracted off this part, essentially, to get the relative kinetic energy. So the relative kinetic energy then looks like gamma minus 1 times mc squared. So still it has that mv squared kind of look to it. And inside the gamma we have the v still, so it still has that v squared look to it. If you're going at certain speeds, at very low speeds, so if at very low speeds your gamma equals 1, and then if you plug in this into this equation here, oh, sorry. They actually do a little calculus trick here. They do a binomial expansion. So they do a binomial expansion of gamma, and they get 1/2 v squared over c squared, and then they plug it in, and they get 1/2 mv squared, which means that your relative kinetic energy at slow speeds is the same as your classical kinetic energy, 1/2 mv squared. So they're showing again that Newtonian physics is still true using this theory. That's important because Newton assumed it was, right? Newton said that it would be. What's that? Sorry, Einstein said that it would be, yes. So. But let's calculate now the classical kinetic energy and the relativistic kinetic energy for a particle moving at very, very close to the speed of light. So if you have something going at 0.99 c, we want to calculate the kinetic energy. We'll do it in mega electron volts because it's easier to do it that way. In mega electron volts, the speed of light is a different number. Let's see, they give it to us here somewhere. The speed of light in mega electron volts is 1, I believe, yeah. So no, that's not right. It's not 1, it's 1 point. It doesn't really matter because they told us the velocity in 0.99c instead of just whatever it is. So anyway, it doesn't matter what it is because it's going to make this easy anyway. But we do need to know the conversion to let's see. Oh, here they do the conversion from electron volts to joules. So here's the conversion from mega electron volts to joules to calculate the relative kinetic energy in joules or in mega electron volts instead of joules. So anyway, we plug in our speed here, and you can see the 0.990c becomes whatever it becomes squared, and the c squareds cancel out, and you get whatever 0.99 is squared. 1 over that, you get gamma is 7.0888. Plug that into the equation, relativistic kinetic energy. And you get 4.99 times 10 to the minus 13 joules, which is 3.12 mega electron volts for the relativistic kinetic energy. But the classical kinetic energy is 0.251 mega electron volts. So the classical kinetic energy is much, much less than the relativistic one is. And that's because the closer you get to the speed of light, the more energy it takes to get it to go faster, right? So in relativistic, it calculates it correctly. And this has been confirmed over and over again. Whenever you're trying to calculate how much energy you need to accelerate a particle to close to the speed of light, this one always works. This one is way off. You need a lot more energy than you think to do that. So, that's relativistic energy. Have we done everything for this chapter?
I believe so.
All right. And like I said, this stuff laid the groundwork for everything after it. Even though relativity does not explain what happens in the quantum world, Einstein's studies of relativity led to the ideas of the quantum world. Okay, because through Einstein's studies, one of the things that he studied was actually not necessarily wasn't related to relativity, but he was trying to study light in general. And one of the things that he studied was the effect of electrons, or sorry, the effect of light shining on a metal. If you shine ultraviolet light or X-rays on a metal, high energy light on a metal, electrons pop out. But not just any old electrons, electrons that have certain kinetic energies, specific kinetic energies. And he explained that in one of his papers in 1905. And that led directly to atomic physics, which we're going to learn in the next chapter. And radioactivity.
So we're skipping 29?
Sorry, it's led directly to quantum physics, which is 29. I meant quantum physics, which also led to atomic physics. And then radioactivity and nuclear physics, which comes from quantum and atomic, was also something that Einstein was able to describe.
Oh, Einstein, the existence of modern physics.
Yes. We owe Einstein everything when it comes to the existence of not just modern physics, but modern science. It affected every science across the board because every science has something to do with chemistry, and chemistry has everything to do with atomic structure. And this is everything to do with atomic structure. So chemistry was extremely affected by it. They already knew all the things that Einstein described and explained, but they didn't know why. They didn't know all of the things. They knew many of them, but they knew that they knew that atoms behaved the way that they do, but they didn't have any clue why. So they weren't able to expand their theories into other realms. They weren't able to learn more. And so everything that chemistry has done in the past 100 years has been because of this. Everything that they know about, for example, valence shells and the different types of, the different shapes of the valence shells, the angles that are between molecules, all of that stuff is known because of Einstein. And so we owe a lot of, and just about everything else that has been discovered has been from chemistry or physics.
Whenever you're dealing with like 10 light years away.
What's that?
Does trigonometry still work correctly when you're dealing with like 10 light years away?
Sure.
I mean, is it correct because of like gravitational waves and that kind of thing?
Well, Sure, because our trigonometry works in this bending universe that we live in. Now, if you want to do your mathematics differently and figure out where it is relative to whatever our universe exists in, then you're going to have to be Einstein and figure out a new mathematics, which he did for his general theory of gravity. That's a good question, because Einstein couldn't explain his general theory of relativity until he created a new geometry that could bend and could warp and could change. And so he worked with a whole bunch of other really smart mathematicians and stuff and created a new geometry. When Einstein said this quote that everybody loves to quote, which says, "Whatever your problems are with math, I assure you my problems are greater," he wasn't saying that he struggled with math. Einstein did not struggle with math.
Well, he did.
At the-
He chose other problems.
At the age of 12, he knew more about calculus than anybody on earth today. Okay, maybe not the age of 12, but maybe the age of 16. He knew more about the most advanced mathematics that we do today, that most people talk about today, than anybody on earth today knows. He was well beyond that at that point. When he entered college at the age of 16, or whatever he was, he knew more than all the professors there about mathematics. He went to class once and then stopped going because his professors didn't like being corrected. And so he stopped going to class. Einstein was a brilliant mathematician, just a brilliant human being in general. And Packer is right. His problem was that he chose to solve problems that were unsolvable using the math that existed at the time. And so he had to invent new mathematics, and he wasn't sure how to do it. So he went to these people that studied nothing but math and tried to, and geometries, and tried to work with them to create a new form of mathematics. And you talk about confusing mathematics. They had to invent tensors, which are essentially matrices that have multiple dimensions. So, we have a matrix that's, rows and columns. Imagine that in every element of every row and every column in your matrix, you had a file cabinet full of other matrices of rows and columns. That's kind of what tensors are like for Einstein. Tensors had multiple dimensions up to, I think, 9 dimensions or something like this. So imagine doing geometry in 9 dimensions. You can't imagine it. There's no way to visualize that, really. But there is a way to do the math. You can do the math even if you can't, graph it. But that's what the universe is like. The universe is like a 3-dimensional, technically we live in a 4-dimensional universe that exists in a 2-dimensional plane. It's like a 4 dimensions inside of 2 dimensions, or something goofy like that.
Maybe our understanding is 2-dimensional.
Well, maybe. But, we can do the math even if we don't understand it. The math is doable. But Einstein was the first one to do it. He was the first one to figure out that it can be doable. He was even the first one to imagine something that needed to be done in this way. And so when he started thinking about, because so far the theory of relativity, as we've discussed it, still assumes that all observers are going at constant velocities in one direction. But that is just not true. We're all rotating and spinning and turning and warping around in weird different directions. None of us are going in straight lines at a constant speed. That's just a lie. But eventually Einstein was able to figure out the mathematics for any observer moving in any direction, accelerating, decelerating, spinning, whatever. He's able to figure out that math. And what he figured out from that math was that gravity is the big thing in the universe. Gravity is what bends space. Gravity is what causes forces. Gravity actually warps space, and then the planets follow those warpings. They actually follow those bends and curves. And that's why planets orbit around the sun. The sun is like a big, massive weight in the center of a trampoline. And marbles are the planets going around and around this bent trampoline. And that's the reason they go around. If the sun wasn't there, they'd just go straight across the trampoline.
It's bigger and faster thing, it gets less of your time.
And this is why I bought, how many yards of spandex did I buy? I think about 10 yards of spandex or something like this at Hobby Lobby last week, and this big steel frame that I'm going to make. And that was going to be our lab this week, but since we skipped our lab this week, it's not going to be our lab. So we're going to make our own gravity trampoline in here. It's going to be like, we want to make it like 7 or 8 feet across, and we'll stretch Lycra fabric over the top of it, and then we'll put big masses in it. We'll fling little marbles in it and let them go around. And I'm thinking that's what I want to take to Ogallala next week. Just do a little. We're supposed to be showing them what you can do if you're a physicist or an engineer. So I figure if you're a physicist, you essentially get to play with toys, whether they be lasers or LIGO interferometers or satellites or rovers on Mars. Physicists get to play with toys. That's what they get to do. So we'll bring a toy to play with. And then if you're an engineer, you make the toys that physicists get to play with, or you make buildings or some other thing. Right? You make the toys that the army shoots, that the armies plays with, and you make the toys that physicists play with, and you get to make the buildings that everybody lives in if you're an engineer.
Better do smart stuff. I'll be physicist.
We'll probably bring the 3D printer along with us too, the small
Big
one. We'll bring the small one with us.
You got a program written for it to make something?
Oh yeah, I've got all kinds of programs written for making things on that one. I usually make the same thing every time. I've got this little cup that I can make. The reason I make it is because it's fairly representative of the things it can do, and it's also very quick and easy to make. So I can make them, and I can even hand them out sometimes at events, because I can make one in about 30 minutes. So it's not that hard to make. All right, so anyway, that is that for this chapter. We've learned about Einstein's theories of relativity. Actually, when I was in college, my teacher for modern physics, which is where you covered these things when you're a physics major, you cover them in a different class. My teacher for modern physics actually he actually had us write a story in the genre of Sherlock Holmes, in the Arthur Conan Doyle genre, that uses physics to commit a crime. Because, of course, Sherlock Holmes, in the Sherlock Holmes books, actually admits that he knows nothing about physics.
That's funny.
But he knows a lot about chemistry.
You throw it up, and the gravitation of the earth makes it spin around, and you hit this guy like 3 states away.
Well, it has to be feasible, and I actually came up with a story that was really quite feasible. In Einstein's general theory of relativity, one of the tenets, the main tenets of that theory, is that there is no difference between acceleration and gravitation. That in the grand scheme of the universe, acceleration and gravitation are the same thing. So if you're accelerating because of some kind of gravitation, not because of your falling, but because of some warp in the universe, essentially. Right? The more the bigger the force causing the acceleration, the bigger the warp. So if it's a bigger force, if it's a small force requiring your acceleration, it's a very small warp, and kind of thing, this kind of thing. But essentially what it is that you cannot tell the difference between a gravitational field and an acceleration. If you're the one feeling the acceleration. So the example of this, the best example of this that I could think of, is when Disneyland made their Star Tours exhibit. Have you ever been on that one? So it was, I don't know if they still have it, I don't think they do, but way back in the 80s and the 90s, Disneyland made a Star Tours exhibit, which is essentially licensed from Lucasfilm, which is kind of funny now since they own Lucasfilm. But they licensed from Lucasfilm's Star Wars footage that had been taken during the first Star Wars film, when specifically when you're flying around the Star Destroyer, not the Star Destroyer, the Death Star, in the around that big mechanical thing, and then they built a big room that was on hydraulics that would simulate the movements inside of the spaceship. so that when you were seeing it on the screen and you were sitting inside of this room, it would jerk you around and accelerate you around, but it would feel like you were feeling these movements as if you were in a spaceship, right? Well, you could also make somebody feel gravity in something like that. Like when you go up a hill, you feel gravity pulling you back towards the back of your, you feel gravity makes you feel like you're falling back towards the back of your car if you go up a really steep hill. Well, you could do that in a room as well. So the story that I wrote had somebody being kidnapped and then being taken somewhere. They were blindfolded and gagged, and they were kidnapped, and they were put inside of a carriage, because this was supposed to be during the time of Sherlock Holmes. And then they were taken somewhere in this carriage. And this person in this carriage keeps track of everything that happens to them in the carriage, all the bumps and the speeding up and slowing downs and the turns, because you can feel a turn as you feel yourself being pulled to one side of the carriage or the other, or going up a hill and down a hill. But in reality, what these people had done is they had put him inside of a contraption that they could lift the sides of. So they were using gravity to simulate accelerations, because you can't tell the difference between gravity and accelerations. So they tilted it to the side, and he felt gravity to the side, and he thought he was being accelerated to the side. They tilted it back, and he thought he was going up a hill or accelerating really quickly or something like that. You know, if you tilt it back really quickly, it's like the horse jerks forward very quickly. Whereas if you tilt it back for a long time, very slowly, it feels like you're going up a hill. So they simulated all of this, and he never left the place that he was kidnapped from.
One of the books in Parsons are Arthur Conan Doyle. They actually took the guy like 5 miles out.
Yep.
And made the path back.
Yep. That's a good one. I have all of his books. I have 3 copies of all of his books, actually.
I read them all.
Yeah, they're great books. If any of you have not read Sherlock Holmes books, the Sherlock Holmes stories were actually published in magazines, in the Strand magazine in particular, except for 2 of them, I believe. And they are the actual reason that CSI units exist. Because before Sherlock Holmes came along, before Arthur Conan Doyle wrote his books, there were only a few people out there that were studying crime scenes using science, and Arthur Conan Doyle was one of them. Arthur Conan Doyle was a doctor, and his mentor, who was also a doctor at the med school he went to, they were some of the first 2 crime scene investigators, and they were doctors. They weren't policemen. They were doctors. They were actually trying to track down what was that famous killer's name?
Jack the Ripper.
No, Jack the Ripper.
Oh, okay.
They were actually trying to track down Jack the Ripper at that time.
There's a TV show about that.
There are a couple of them actually.
There's actually a really good one out right now.
There's one out right now, I don't think it follows Arthur Conan Doyle's story. But there's one that came out a few years ago that is an actual story that comes from his actual journals, that talks about them trying to track down Jack the Ripper. And of course, they never caught him, but they came closer than anyone else because they found all kinds of evidence pointing to this person. So, but this is the only reason that police do this today, is because of these books being written. Nobody did it at the time except these 2 doctors. So, all right, next week we'll do quantum physics, and we'll be moving on through the chapters here. We do have homework up and running though. I'm going to try to get in and try to code some real problems for next week. And actually for that test, I'm going to try to code that problem as well. That's the first one I'm going to try to code. So I'll try to code that problem that's on the test, and then I'll give it to you again so that you can do it. You're welcome. And then I think when are you going to take the test, Barry?
Monday.
You're going to take it Monday?
I have it scheduled.
Okay, somebody else is taking it next Tuesday, I think. I think Sam is. And then,
How about you just give me 0.2 for the test and we'll call it 0.2 for that problem.
you just want 0.2 out
For
of
me
1?
giving you the information about that, maybe the problem with your test.
You not trust your ability to just do that.
Why don't you just do the problem and get 0.2 out of it?
Because 0.2 would make my score 93, I think.
You're good set up for
I think the grades in this semester are just too easy. I'm going to make these homework problems harder next year. You guys have made up my mind. My homework problems aren't hard enough.
Hey, he's the dumb one in the class, all right? That should tell you what you're up against here.
Point at the kid half your age. That's nice of
right.
you.
I got to. You're going to pick on somebody, pick on the small guy. Right.
I'm offended.
I'm sorry.
All right. Did you see Packer's new jacket there?
I like that.
Yeah, it's like really cool.
Except it doesn't have any bullet holes in it or anything.
Yeah, it's such a second.
Are any of the holes in your jacket from bullets?
Not the black one, but the one I other one where I did it interesting.
I know it. Bombs blowing up and bullets coming at you. They're actually trying to develop a. They're trying to build a or organize, I guess is a better word,